Hey everyone! Today, we're diving deep into the fascinating world of neutrinos and their role in understanding Earth's mantle. We'll explore how a global constellation of neutrino detectors is providing a never-before-seen view of the radioactive elements that power our planet's tectonic heat engine. So, grab your headphones and let's get started. First things first, let's talk about neutrinos. These particles are the most abundant mass-possessing particles in the universe, but they're incredibly elusive. They barely interact with other matter due to their tiny mass and neutral electromagnetic charge. Trillions of neutrinos pass through our bodies every second, yet scientists have only captured a few 100,000 of their precious flashes. And then there are geoneutrinos, which are even more elusive. These are produced by processes that heat the Earth's interior, playing a crucial role in powering the flow of rocks in the mantle. This heat comes from two main sources, the planet's formation and the decay of uranium, thorium, and potassium in the mantle and crust. Now, let's talk about the SNO+ experiment. This massive detector is buried deep within the Creighton mine in Sudbury, Canada. It's designed to catch geoneutrinos, and it's located in a cavern filled with 7,000 tons of ultrapure water. The experiment is a massive acrylic sphere lined with 10,000 sensitive light detectors and filled with 780 tons of oily liquid scintillator. This setup allows the detector to catch the elusive geoneutrinos, which are produced by processes that heat the Earth's interior. The first detection of geoneutrinos was made by an instrument in Japan called Kamland in 2005. In 2009, the Borexino detector in Italy reported catching several dozen more. And in November 2025, SNO+ reported its first detection, significantly increasing the number of observed geoneutrinos. What makes SNO+ special is its location in the Western Hemisphere, offering a new perspective on Earth's radioactive interior. However, there are major uncertainties in interpreting the results from these experiments. Researchers' best estimates suggest that each site is measuring a different flux, which could indicate that the mantle is not uniform. Geochemists have traditionally assumed that radioactive elements are evenly distributed throughout the mantle, but the measurements of geoneutrinos in different locations might suggest otherwise. The regions producing the most geoneutrinos seem to sit above continent-sized blobs of anomalously hot, dense material known as large low-shear velocity provinces, LLSVPs. These structures are located on either side of the Earth's core, with one under Africa and the other under the Pacific Ocean. This could mean that there are deep Earth structures in the mantle that are not yet understood. Neutrinos could provide new insights into the origin of these deep structures and the patterns in the mantle that underlie many aspects of the Earth system. It could be a way to create a chemical map of the Earth's interior. But there's still a lot of uncertainty surrounding the geoneutrino measurements. The question remains whether the geoneutrino measurements reveal differences between the areas of the mantle below each experiment or if the imbalance originates in the way the different experiments count their geoneutrinos. There's still so much uncertainty that it's impossible to say for sure. The detection at SNO+ comes at an exciting moment for geoneutrino research. Another huge neutrino experiment, Juno in China, is expected to report its first geoneutrino flux later this year, adding a fourth and notably richer view. With its massive size, Juno is expected to detect more geoneutrinos in its first year than the combined output of Kamland, Borexino, and SNO+ over decades. To get clearer estimates of the geoneutrino flux at each experiment, we need more detailed geological data and further geoneutrino counts at each site. However, one of the best solutions, according to geochemist William McDonough, would be to build a neutrino detector at the bottom of the ocean. This would eliminate crust-related uncertainties and provide a more uniform and accurate view of the mantle. The idea of an ocean bottom detector has seen little support from government funders so far, but McDonough is hopeful that he can make it happen in China, which has given the green light to other big geoscience projects. Until then, physicists will continue their quest for answers deep underground. Thanks for watching. I hope you found this journey into the world of neutrinos as fascinating as I did. Don't forget to like and subscribe for more amazing content, and stay curious.